Hi there, guys. Well, we're at the point where we have two more exercises left. We have U and V, 4U and 4V, which is quite nice to leave UV to the end of a unit on differentiation, where U and V turns up in a lot of these formulas. Okay, well, this is about implicit differentiation and related rates of change. Now, I'll deal with this rather than through the formula, just by dealing with a particular example. But just to say that related rates of change are often those applied types of questions which can be seen as a subset of implicit differentiation in its entirety. So you can do pretty much all of these questions if you know implicit differentiation, although related rates of change is like a subset of that as well. But both of them as well are just little extensions on from the chain rule. Okay, so really we're extending the chain rule here, and this is pretty nice, to be honest. Let's just take something, and so it's taking things like, oh, check it out. Here's a crazy looking graph which can be split into many functions, and they can come from equations which look something like this. Where we've got x squared and y's all wrapped up inside it. And then look at 5b here. It's got x cubed, y cubed, minus 9xy equals 0. And you're thinking, well, how on earth do you differentiate that if you can't rearrange it to make y the subject? Well, this is where implicit differentiation comes in. So we can essentially now, we're going to be able to work out the gradient on any point on a graph, not just a function. Okay, so let's take one of these, and let's take the one which they use in the book. Let's just zoom in massively here, and let's take this thing. That's what we were working on last time around. Let's take this thing here. And what we're going to work towards is finding dy dx. Let's actually work out what this looks like. So we've got 2x squared plus y cubed. Okay, so check it out on Desmos. So we've got 2x squared plus y cubed. 2x squared not equals plus y cubed, and then it was equal to, what do we got? We've got equal to 3x. Oh, nice. Okay, so this one kind of looks like a function. Might be the case that there's two values which are, if we zoom in here, maybe this is kind of a vertical line at some point here. I don't know, which obviously wouldn't be allowed, but actually it looks a little bit like a function, to be honest. Quite an interesting little thing. Okay, well, we've got this, and we could rearrange this to say, well, look, we've got y is equal to 3x minus 2x squared, and then take the cube root of this. And then we could think, okay, well, yeah, that is a function. That's definitely a function because we can write it like this. And then we could try and use the chain rule to differentiate this. Now, I'm not going to do it via that approach, but you should end up with the same answer as this approach by implicit differentiation. Now, implicit differentiation, what is it? Right, it's saying just apply d dx to whatever gets in the way, whatever term there is. Differentiate, use d dx as an operator. Okay, so let's do d dx of everything. Let's d dx it all. So we've got 2x squared there plus d dx of y cubed, and is equal to d dx of 3x. There we go. Okay, now there's certain bits here which we can do straight away. So I can see that here we can do, let's differentiate this function here. So where I'd normally say dy dx, well, this is our y. So let's bring the 2 to the front. So we've got 4x, that's pretty easy. And it's pretty easy on the other side as well. Look at this. The derivative of this is just 3. So how do I differentiate this thing? Well, a lot of people might think that you just do 3y squared and leave it like that. But you can't, because y is of itself a function of x as well. So what we're really trying to do here is d dx, take the derivative of not just y, but a function of y, and that function of y is y cubed in this case. Okay, but what we're doing is we're actually getting some function of y, which is a function of x. So we need to use the chain rule. So normally we don't write this though, we normally write, rather than having y here, when we're using the chain rule, we normally call it u of x in the center. And we can either say that's f of u of x if you like, that's to say we've got a function of u of x. You know, like for example, f2x plus 1 cubed, that's saying u cubed. Okay, so in order to do this, we realize let's take all of this back. So in order to differentiate the y cubed, we're going to need to do, well, that's our function if you like. So, you know, normally we call y the whole function, but, you know, maybe we can call that f of x. So what we're going to do is sorry, f of y. So we're going to do differentiate f of y with respect to y, and then we're going to differentiate y with respect to x. So where we'd normally have du dx in the chain rule, we've here got dy dx. So what are we doing? We're trying to find here d dx of f of x. Okay, so that's what we're looking for. We're looking to differentiate f of x with respect to x. Here is f of x, it's y cubed, but we can only differentiate a function of y in terms of, or with respect to y. So then in order to create a dx, we're going to need to put on the end this dy dx. And now that dy is essentially cancelled, although we know from that that's not strictly true, these aren't really fractions, but we can think of it like that. And we end up getting the derivative of our function of y with respect to x. So in order to do this one here, so let's just take a bit of that back. Okay. So when we're doing this, we're going to need to differentiate, you know, y cubed with respect to y, and then times that by dy dx. Well, y cubed with respect to y is going to give us 3y squared. Oh, like the thing we kind of expect. But then we've got to remember to put on the end that dy dx. Okay, and then we can just rearrange in order to work out what dy dx is. So dy dx is now equal to 3 take away 4x divided by 3y squared. Okay, and there we go. That's our final function. Now we have our derivative of y, so our graph y here, or our function y. So we've got our derivative is now in terms of both x and y. Okay, now again, if you could rearrange this equation in and put it in terms of y, then you definitely could then substitute that. Rearrange this equation to make y the subject, and then put it in terms of x. Then we can definitely replace the y there with that rearrangement. But it's not always easy to do that, and so that's the issue that we have here. And so it's fine to leave things in terms of x and y, but this is just done what's called implicitly differentiated. So it's in terms of both of the variables. So now if I put in a coordinate point, say for example I put in the coordinate point, let's look at the graph actually. So we see, here we go, we can see, let's put in 1, because we can see the gradient of 1 is kind of slightly negative. So let's put in 1. Now when we put 1 into the function here, okay, well we're going to need to solve that, aren't we? So we'd need to put 1 into here for x. So we get 2 lots of 1 plus y cubed equals 3 lots of 1. So in other words, y cubed is going to be equal to 1. So y is going to be equal to 1 as well. So we've got this coordinate point, 1, 1 on the graph. Now if we substitute those things into here, we're going to see that we get 3 take away 4 divided by 3 when we put the x and the y parts in. And that's going to give us minus 1/3. So at this point here, when we put in the point 1, 1, we have this gradient of minus 1/3. So minus 1/3 x. And then, you know, if I put a c on there, I can just add a slider, then just, we can pick that up and find the spot there just to show you that that's the tangent at that point. Okay, so that's the gradient at that particular point, and we've done it through implicit differentiation. So let's have a little look what the book says. So the book is doing exactly the same as what we're doing there. And it says, actually, there's another way of dealing with this, and that's using the rearrangement. So you can see on this line here at the top, we can see that they've done a rearrangement. And again, you could find your derivative from using the chain rule with the rearrange function there as well. And so they actually haven't done that, but they've done it further down the page there as well. What they're talking about there is actually just rearranging for y and then substituting it back into our implicitly differentiated function. Okay, but it's the same as what we've been talking about. Okay, so let's see if there's any little boxes that we need to take note of. Box here, it says, when differentiating a term u of y, so some function of y with respect to a different variable x, the chain rule, d of u of y, and now we looked at y cubed as u of y, but I didn't call it u of y, I called it f of y, was f dash of y when we're differentiating with respect to y, and then doing dy dx. Now they've used u there, we used f. Okay, but there you go, same. Let's get some practice with this then. So it's example 37, and then we're straight into the exercise. So example 37. Okay. So differentiate with respect to x the Folium of Descartes. For this thing here. Okay, let's put it into Desmos first. Let's just see what this looks like. We've got x cubed plus y cubed, take away 9xy. So got x cubed, take away y. It was plus y cubed, wasn't it? Take away 9xy, not xt, equals 0. Is that right? Yeah. X cubed plus y cubed. Oh, check that one out. Beautiful. Okay, lovely. Okay, and that was actually the shape which we were looking at the start through the investigation. So that's this one here, the Folium of Descartes. Okay, well, I really like that graph. That's pretty geeky. Okay, so there's the graph. That's what it's looking like. The Folium of Descartes seems to have some slant or oblique asymptote there. Don't know if that's true or not, but okay. So there we go, there's our shape, and we're trying to differentiate this implicitly. Okay, so let's deal with this then. So we've got d dx of everything which we see, so of x cubed plus d dx, an operator on y cubed, and then minus d dx of 9xy. Okay. Now, first part is easy. We've got 3x squared. Second part is easy now too. We've got 3y squared times by dy dx. Okay, that's just the formula which we talked about before. Of course, we're saying let's differentiate this with respect to y, and then the dy and the dy essentially cancels, and then we've got to have the dx back because we're doing this in terms of dx. Okay, now we're looking at this part here, and we're thinking, how do you differentiate this function? Now let's just take out the minus 9. So we're really asking, how do you d dx x, y? Obviously, we can take out constants from derivatives, no problem. Okay, so we've got to do this still. Now that's a product. So we're going to need to do u equals x, y equals, sorry, v equals y, v equals y, and then we're getting u v dash plus v u dash, that's going to be our derivative of our d dx of x, y. That's what we're getting. That's the format we need to put it in. So we're going to put in u, which is x, and the derivative of y with respect to x is just dy dx. Now, if this was y squared, or if it was y cubed, we'd have to write this. We'd have to use the chain rule here again, because we want to differentiate a function in terms of y with respect to x. Okay, so we've got x dy dx. So dy dx is just, let's differentiate this with respect to x, and then plus v u dash. Okay, so v is y, and u dash, so du dx, is going to be just 1 there, so we can just leave it like that. So this is what we need to substitute in here. Okay, so now we're getting 3x squared plus 3y squared dy dx, which hopefully will cancel out, we'll factorize out later. We've got minus 9, lots of this thing here, so that's 9x dy dx, and also minus 9y there. Okay, minus 9y, so I've just multiplied that out as well, saving myself some space, but obviously use as many lines as you possibly can. Right, so now let's factorize out dy dx. So we've got dy dx. Oh, let's write it down here. Okay. But dy dx now factorized out. It's going to be factorized out of the two terms. We get 3y squared take away 9x. On the other side, we can take this across, and we can take this across, and we can get 9y take away 3x squared. Now, of course, the only thing which we need to do after that is do a division. So we've got 9y take away 3x squared, and we've got 3y squared take away 9x. Oh, it looks like there's some symmetry in that answer as well there. Okay, then it says find the equation of the tangent to the curve. And I'm conveniently running out of room here. So we put 2, 4 in here, so we can put 2 in there, and 4 in there, 4 in there, and we're going to put 2 in there. And then we need the equation of the tangent. So we also need the coordinate point, of course, and we're going to need, for the equation of the tangent, we're going to need the gradient. So we're going to need m. So we're going to get m when we substitute in 2, 4. Okay, well, I'm going to just cheat here and check out what they get when they put that in. So they're getting out 4/5. Okay, and in fact, it's pretty easy from there. I might not actually do that. So we can see that they're getting 4/5 from substituting the numbers into here. So that's giving us our m is equal to 4/5. And then they're combining it with the 2, 4 and making the equation of the tangent. That's pretty easy to do. We set up y equals mx plus c, put in your xy point, and you'll find what c is. Now, let's just have a look. They've used the point intercept form there, you can see, but you can also just use y equals mx plus c. And in the last line, they've just come up with the form which they've asked for at the start, ax plus by plus c equals 0. And of course, you could also have that as the minus 4x, the plus 5y, and the minus 12 all taken to the other side. Okay, well, we've got minus 4x plus 5y. So it's minus 4x plus 5y, and I think it was minus 12, wasn't it? Equals to 0. So let's just check that again. And minus 12 is equal to 0. And that was the tangent to the point, no, I've forgotten that, to the point 2, 4. Okay, so to the point 2, 4. So where's 2, 4? So that's there. Okay, so there we go. That's what we've just found. And, next part of the question might say, well, where else does the tangent cut the curve? So you'd have to solve this equation with the other equation of your straight line, for example. But okay, really nice. So what was really important about this question, and why this was different to the first question which I chose there, was that this term had to be treated by using the product rule. And sometimes you'll get more complicated rules there. So sometimes if you had minus 9xy cubed, then realize that when we're differentiating this, it's going to give you this when you're differentiating it with respect to x. So it could definitely be more complicated there. It turned out for us that when we were differentiating this with respect to x, it just gave us dy dx. Okay, right, good. Well, we're coming up to 4U now. 4U is all implicit differentiation, of course. And the next bit that we're going to be dealing with is the related rates of change. And there'll be two ways of doing this. And I imagine they're dealing with it essentially by looking at using implicit differentiation, so developing that one on. Okay then, guys, well, thanks for listening, and hope to see you back for the last one.